Hi everyone, this is Dr. E. Sridevi, Professor, Department of Electronics and Communication Engineering. In this video lecture, we are going to learn about electric dipole. On completion of this video lecture, the learners can able to understand the basis and applications of electric dipoles and dipole moment. First of all, we have to know what is an electric dipole. An electric dipole consists of two equal and opposite point charges. One is plus q and another one is minus q. These two charges are separated by a small distance which is called as 2a. An electric dipole consists of two equal and opposite charges separated by small distance is the definition of dipole, and it is the fundamental concept in electrostatic and electromagnetic theory. Plus q is the positive charge and minus q is the negative charge. 2a is the length between plus q and minus q is called as dipole length. Next topic is dipole moment, that is represented by the letters P. Dipole moment is a vector quantity which is defined as P is equal to Q into 2A into L, where Q is the charge and 2A is the distance between charges. L is the unit vector between plus Q and minus Q. The unit of this electric dipole is coulomb meter, C into M. Direction is from minus Q to plus Q. An electric field due to dipole is defined as that is E axial. We have to consider an electric dipole placed in free space to measure the electric field E due to this dipole. So points on the same lines as the dipole is called as dipole axis. So E on dipole axis is known as E axis is equal to 1 by 4 pi epsilon naught into 2 rho P divided by R square R cube or otherwise R square into R, that is we can write it as R cube. P is called as dipole moment. Epsilon naught is the permittivity of free space. Direction is along P. Electric field on equatorial line. So points perpendicular to dipole axis, E equatorial is equal to 4 pi epsilon naught into P divided by rho cube. Direction is opposite to dipole moment, that is P. Torque on dipole in uniform electric field is represented as tau is equal to P into P cross E. P is the dipole moment or dipole length. Tau is equal to P into E into sin theta. If theta equal to 0, torque equal to 0. If theta equal to 90 degree, torque equal to maximum. If theta equal to 180 degree, torque is equal to 0. So theta is equal to 0 means it is called as stable equilibrium. For 90 degree it is called as maximum, and 180 degree the torque is called as unstable equilibrium. And dipole moment is a vector and the direction is from minus q to plus q, and electric field decreases as 1 by r cube. Torque tries to align the dipole with field. Potential energy is minimum when aligned with the field. Potential energy of the dipole U equal to P minus P into E, that is U equal to minus P into E cos theta. So electric potential due to dipole is given by the formula V equal to 1 by 4 pi epsilon naught into P cos theta divided by R square. So how the dipole is formed? A dipole is formed when positive and negative charges are separated. At that time the dipole is formed. It is its moment, dipole moment is measured as P is equal to Q into D. Q is the magnitude of charges and D is the separation between charges in meters. Unit of dipole moment is called as coulomb meter, and the direction is from negative to positive charge. Potential due to a dipole. The potential at the point due to the dipole is given as V. V is noted as V is equal to 1 by 4 pi epsilon naught into P cos theta divided by R square. This shows the potential difference as the square of the distance from the dipole increases. Electric field due to dipole is represented as E is equal to 1 by 4 pi epsilon naught into 2 into P into cos theta divided by R cube. The field decreases as the cube of the distance from the dipole. Axial and equatorial points. The axial point lies on the axis of the dipole. Equatorial points lies on the plane perpendicular to the dipole axis, and the field directions are and magnitudes differ in these two cases. Electric field on the axial line. E axial is equal to 1 by 4 pi epsilon naught into 2 into P divided by R cube. This is directed along the dipole axis from positive to negative charge. Electric field on equatorial line is called as E equatorial equal to 1 by 4 pi epsilon naught into P divided by R cube. The direction is the field opposite to the dipole moment. Torque on the dipole is known as tau is equal to P into E sin theta. This torque tends to align the dipole along the field direction. The potential energy of the dipole in electric field U is equal to Pe cos theta, the minimum potential energy when dipole aligns with the electric field. Work done in rotating the dipole is called as W is equal to Pe cos theta 1 minus cos theta 2. These are the important formulas related with dipole and dipole moment. And dipole in non-uniform electric field is denoted as the field experiences force and torque. The force is denoted as F equal to P into delta into E, and flux lines is given as the direction of electric field, and it originates from positive charges and terminates on the negative charges. Equipotential surfaces have the same electric potential at all points and they are perpendicular to electric field lines. The properties of equipotential surfaces are the no work is done in moving the charge on an equipotential surface. It is closer indicates the stronger electric fields. So relation between flux and equipotential lines are the flux lines are always normal and equipotential surfaces, and the relationship helps to visualize the electric field structure. So while talking about the applications of electric dipole, it is used for measurement of dielectric properties, polarizations in materials, antenna design and field mapping in medical devices. And dipole approximation when R is greater than D, the field of any charge distribution can be approximated by that of a dipole. This simplifies the analysis of complex charge systems. So to overall, dipole consists of equal and opposite charges, produces the characteristics electric field and potential. It is important in understanding electrostatics, molecular interactions and the practical applications. Hope you all understand this session. Thank you for listening.